Welcome to the alternative format of our design presentation amid this COVID-19 pandemic. My name is Hamza, and together with Abdul, Connor, Daniel, and Safan, we will be presenting a summary of our research towards the development of a power-assisted mobility device for manual wheelchair users. This presentation is broken up into 5 subsections which are presented on screen. Additionally, the speakers and associated slide numbers for each section have been included for your convenience. This first section aims to identify and provide the necessary background information to quantify the problem that we are solving. As of 2018, there were approximately 4 million people across Canada and the United States who required the use of wheeled mobility devices, with this figure expected to increase over the next few decades. The bulk of these individuals are manual wheelchair users. Due to the physiological demand associated with propelling oneself in these chairs, many users reportedly develop secondary complications which further deteriorates their health and quality of life. Current solutions are to switch to a powered wheelchair or get a power-assisted device. However, both of these options have their limitations. Powered wheelchairs are bulky, require lots of maintenance, are difficult to maneuver through tight areas, and are functionless when they run out of power. Power-assisted devices are extremely expensive, are not adaptable to the user's needs, and have limited modularity. Despite this, a power-assisted device is more practical for the needs of a manual wheelchair user provided we address these weaknesses. The scope of this project was to create a power-assisted device for the average manual wheelchair user who has full upper body range of motion. The objective was to create a device that was cost competitive, had adjustable power assist output, and could easily integrate with the user's existing wheelchair while reducing the development of secondary complications that arise with manual wheelchair use. The main design constraints of this project revolved around the power assist device's physical specifications and primary functions. On screen now, you will find a table that expands on each of these constraints. The main design criteria of this project were in relation to the aesthetics, cost, and quality of life features of this device. Again, displayed on screen is a table expanding on these criteria.
Hello, this is Abdel, and I will be discussing our approach to the design. Before selecting our design, we considered 3 design concepts. Our first design concept was a wheel with a built-in power assist. This entails using a common wheelchair and permanently fixing a hub motor to one of the wheels. The hub motor will provide supplementary force by rotating the wheel, which means the user applies less force to achieve the same distance. Our second design concept was a lower body exoskeleton. This concept essentially replaces a wheelchair altogether. A pair of bionic legs are safely attached to the user's limbs. A computer processes nerve signals from the user and translates that data to biomechanical motion, such as standing up, walking, and sitting down. Our third design concept is a power assist module. Unlike our first design concept, this is not a permanent fixture. The power assist module is simply a motorized detachable wheel which provides supplementary force with every user's stroke. In our design evaluation, we considered the following criteria. Most exoskeletons in the market sell over $40,000, and a built-in power assist presents many technical and repair issues because it is a complicated mechanical system with a lot of pinch points. Our design matrix and sensitivity analysis demonstrate that a power assist module is most feasible. And now, Daniel will talk about our design solution.
This section provides a simplified description of our final design solution. Our power assist device is designed to attach underneath any manual wheelchair and provide continuous power to supplement the user's own driving force using the push rims. It is comprised of 3 main components: the power assist module, which provides the driving force, the hinge mechanism, which attaches the module to the chair, and the control panel, which allows the user to view and adjust the module setting.
The power assist module contains the battery, hub motor, and the suspension system, all held together in an ABS plastic casing. There is a charging port located directly on this module so that the device can be charged whether or not it is attached to the wheelchair. The module is designed to slide into the hinge and will be locked in place with a snap fit that has a mechanical button release, as shown in blue. The hinge mechanism is permanently clamped onto two parallel bars directly underneath the seat that are common on all manual wheelchairs. This hinge is comprised of two flaps held in place with a pin. Removing this pin allows the wheelchair to maintain its ability to fold in half without the need for disassembly. Lastly, the control panel is the brain of the power assist device and is responsible for turning the device on or off and controlling power output of the motor.
To use this device, the user will turn the dial to select the power assist level that they desire. The user turns the device on and uses the wheelchair as they normally would. The difference is that between each push by the user, the module extends the coasting distance. Additionally, due to the momentum this creates, each push of the push rims requires a smaller amount of force. As a result, the amount of pushes and force required to keep the wheelchair moving by the user is decreased and ultimately result in less physical strain.
In this section, I will validate the quality and impact of our design. First, for functionality defense, the device should assist in overcoming the force of rolling resistance. According to the U.S. National Library of Medicine, the average manual wheelchair user applies 55 newtons to the push rims of the chair during motion. The Power Assist module would reduce this force by 20 to 80% based on user selection. Reducing this force lessens the stress applied to the human body itself as a result. As discussed on the previous slide, the Power Assist module reduces the force that the user would apply to the chair by 20 to 80%. This reduction provides health benefits to the user by lowering the chances and severity of muscle imbalances. These imbalances can even lead to joint displacement, which could be eliminated by the device. The device also poses no injury to the user once installed. The only possible injuries during installation are minor pinch points, though these points should be easily avoidable if the device is installed carefully. Another important benefit of the device is increased social integration compared to regular manual or electric wheelchair users. While manual wheelchairs require constant motion and more physical effort, the Power Assist module allows the user to focus more on other tasks while using the wheelchair. Additionally, the Power Assist module would allow wheelchair users to travel farther and keep up with those walking around them. Electric wheelchairs are big and bulky, often making users feel like they stand out more than manual wheelchairs, meaning that the Power Assist module fitting into a manual wheelchair would lessen the feeling of standing out that many electric wheelchair users experience. Next, the design needs to be competitively priced compared to alternatives already on the market. To achieve this, the module has been priced at $1,500, significantly cheaper than many high-end alternatives such as SmartDrive, and still cheaper than other competitors. The final discussion for the design revolves around the possible risks to the design. The first risk is whether or not the device would be easily attached to the wheelchair models with dimensions that stray from the typical wheelchair. Additionally, the module would currently require services from the company to repair it, which could prove to be difficult for users, and must be addressed going forward. Finally, even with the lower price of the module compared to alternatives, the device may still prove to be too expensive for widespread use. Without government subsidies in areas of primary distribution, this could hurt the company, reducing distribution and sales.
Our goal as a team was to supply a new solution to the problems experienced by users who use manual wheelchairs. Through the Power Assist, we will have overcome increased strain on user shoulders, that means upper extremity pain caused by manual wheelchairs. Due to this strain, users are not able to cover long distances. The Power Assist module gives increased range of mobility, making it less painful to push. The Power Assist will provide ease of access to the user in several different ways. The module detachable, which makes it relatively easier to repair. There are two charging ports, one on the side of the module and one on the handle to access for aged users, making it relatively easy for them to charge. Incidentally, when the power module runs out of power, the wheel on the module will act as a free wheel. The device is competitively priced at $1,500, which is significantly lower than other Power Assist modules in the market. Our team believes there is always room for improvement. The main priority for everyone working here is safety and quality of life for the users. However, plans to improve the design include decrease the battery size since it makes the module quite heavy, with keeping in mind to increase its capacity to provide users with longer range. Furthermore, work will be needed on software side to fix bugs and deploy patches to make sure power adjustment provides accurate speed. In future, we would like to use more environmental friendly materials such as PLA and recycled aluminum. Further research will be conducted to decrease the size of the module and the risks associated with the product.
With this, we have reached the end of our presentation. Thank you for listening.